All right, hello and welcome to lecture. We're going to be, knock on wood, polishing off chapter 8 and starting chapter 9 tonight, hopefully at least. But in any case, let's go ahead and dive in. I apologize for my my sniffling. It is allergy season is in full swing. And I just got back from a bike ride with my youngest. So, anyways, I will battle through the allergies here. So, we left off talking about the equilibrium constant. Excuse me. And just as a way of reminder, we said that the equilibrium constant generically is a ratio between the concentration of products of a reaction over the concentration of reactants. That this is what the equilibrium constant is, kind of generically. Zeroing in on a more precise formulation, a more precise mathematical equation, if you have a reversible reaction with reactants A and B and products C and D, the equilibrium constant is equal to the molarity of C, capital C, raised to the power of lowercase c, times the molarity of D, raised to the power of lowercase d, over the molarity of A, raised to the lowercase a, and times the molarity of B, raised to the lowercase b. And we noted that these exponents in the expression are our stoichiometric coefficients. And again, that we have products in the numerator and reactants in the denominator of the expression. And that is the mathematical expression for the equilibrium constant. One last quick reminder, these square brackets mean molarity. So this means, or not means the molarity of A. All right, and so that's just a quick review. I know we introduced equilibrium constant at the end of last lecture, and we're going to be using it quite a bit today. So I wanted to just take a moment, put that in the forefront of everyone's mind before we move forward and do a few more examples. So our first example of the day is the following. Calculate the value for the equilibrium constant of the following reaction if the concentration of NO2 is 0.00823 molar, and the concentration of N2O4 is 0.0146 molar at equilibrium. All right, and the reaction being spoke of is the reaction of NO2 gas reacting reversibly to form N2O4, which is also a gas. All right. Now, before we can calculate our equilibrium constant, we need to write an expression, the mathematical expression for the equilibrium constant of this reaction. And we always put products in the numerator and reactants go in the denominator. And then we need to square, we need to square the concentration of NO2 because it has a stoichiometric coefficient of 2. Since N2O4 has a stoichiometric coefficient of 1, we don't need to do anything there. Now, this is the expression for the equilibrium constant. We have both values here, so we can just plug them in. At equilibrium, our concentration of N2O4 is 0.0146, and our concentration of NO2 is 0.00823 squared. You'll notice that I did not include my units when I plugged it in. That's because the equilibrium constant is a unitless quantity. There are no units here for KEQ, so you don't have to worry about including them. All right. Now we need to crunch our numbers. So let's see, we got to go 0.00823, and we have to square that, and then that is in our denominator, times 0.0146. My calculator is giving me a value of 215.55256. We can only keep 3 significant digits. Both our numerator and denominator, our concentrations only have 3 sig figs, so our answer can only have 3. So you count off your first 3. Our 5 rounds up. And so the correct value for equilibrium constant with the correct number of significant figures will be 216. All right, and that is the value for the equilibrium constant for this reaction. All right, now, so we've had some experience at the end of last lecture. We were writing expressions for equilibrium constants. Here we just calculated a value for the equilibrium constant. I want to take a minute and talk about what the equilibrium constant actually means, all right? And the thing to remember is right up here. It is a ratio of the concentration of products over the concentration of reactants. All right, that is a ratio. So if you have a large equilibrium constant, if you have a large number, that means the numerator is bigger than the denominator. So that means that there are more products at equilibrium. If, by contrast, you have a small value for your equilibrium constant, that means that you have more reactants. At equilibrium. And I need to be specific here. When I say small, I mean less than 1. And when I say large, I should say actually, give me 1 second. When I say small, I mean more than less than 1. I should say much less than 1. And when I say large, I mean much greater than 1. All right. So if you have a number that is much, much smaller than 1, that means you have a larger denominator. That means you have more reactants at equilibrium. If you have a number that's much, much greater than 1, you have a larger numerator. That means you have more products at equilibrium. When you have more products, the way we describe it is we say that the equilibrium lies to the right. Because the products are on the right side of a chemical reaction. When you have more reactants at equilibrium, we say the opposite. We say that equilibrium lies to the left. All right, so that's how you kind of describe the position of equilibrium. Large equilibrium, more products, lies to the right. Sorry, large equilibrium constant. Small equilibrium constant, that means there's more reactants, and we say that the equilibrium lies to the left. All right, now this brings us to the final concept we have to discuss in this chapter, and it is known as Le Chatelier's principle. Oops. All right. Now, I want you to consider the following chemical reaction for a minute. Chemical equilibrium, the equilibrium where ammonia decomposes into elemental nitrogen and elemental hydrogen. All right, now remember what it means to be at equilibrium, all right, for a minute here. If you are at equilibrium, we talked about the equilibrium condition last lecture. That means the rate, i.e. the speed, of the forward reaction is equal to the rate of the reverse reaction. That the speed at which ammonia is decomposing into nitrogen and hydrogen is equal to the speed at which nitrogen and hydrogen are reacting to reform ammonia. So you get this constant loop where the two rates are equal, and as fast as one is reacting away, it's being replenished by the reverse reaction. All right, now I have a question for you. I have a question for you. Here's the question. What happens when you add ammonia to this equilibrium? You add extra ammonia. What happens when you add extra ammonia to the equilibrium? All right, now, what that's going to do, if we add more NH3 to this equilibrium, it will increase the concentration. Right? It'll increase the concentration of ammonia. That'll go up. And if you have a higher concentration, will that result in more or fewer collisions? That's the question to ask yourself. At a higher concentration, you're going to have more collisions of ammonia molecules together. That increase in collisions is going to increase the rate of the forward reaction. It's going to increase the rate of the forward reaction and not change the rate of the reverse reaction. So temporarily, what this is going to do is immediately after you add NH3, the rate of your forward reaction is going to be greater than the rate of the reverse reaction. All right? Temporarily, the rate of the forward reaction is going to be greater than the rate of the reverse reaction. So what's going to happen? Now, equilibrium will reestablish itself, but as the rate of the forward reaction now is faster, it's going to start slowing down, slowly, because it's going to be reacting, it's going to be forming, nitrogen and hydrogen, which is going to be slower at the beginning. But as you increase the concentration of nitrogen and hydrogen, it'll start catching up, right? So what we had is ammonia got faster, but then it starts falling, nitrogen and hydrogen start rising until the rates are equal again. And that is the equilibrium condition when equilibrium is reestablished. In order for the rates to be equal, the concentration of ammonia will have to decrease while the concentration of nitrogen and hydrogen will have to increase. In other words, hang on. So if you look at the expression of the equilibrium constant, after adding NH3, this is temporarily too large. So what's going to happen is it's going to react away. This concentration will decrease. These concentrations will increase until to the point where this expression once again is equal to the equilibrium constant. All right, they're going to change, they're going to alter. There's going to be a shift where the reactant is going to become nitrogen and hydrogen until those rates are equal again, and then you've reestablished equilibrium. All right? So there's going to be a shift. We'll say a shift away from NH3 and towards nitrogen and hydrogen. All right? After the shift, after the shift in equilibrium, there's going to be two differences. First, there's going to be more nitrogen and hydrogen, right? Higher concentrations of these, and there will be less, a lower concentration of NH3 because it had to react away. All right, and this is an illustration of Le Chatelier's principle. All right, and we say that this is this shift that we're talking about. We say that equilibrium shifts to the right towards products. All right, this is an example of Le Chatelier's principle. Le Chatelier's principle states that when a system at equilibrium is disturbed, it will shift to reestablish equilibrium. All right, so here is Le Chatelier's principle when a system at equilibrium is disturbed, it will shift to reestablish equilibrium. All right, you add one thing, it starts reacting faster, it will react away until the concentration builds up in the reverse reaction so that those reaction rates are once again equal. One totally legit question at this point is what are disturbances? How do you disturb equilibrium? And I have to warn you, if anyone out there watching is in equilibrium, you might find the following disturbing. A change in concentration of reactants or products is disturbing. A disturbance to equilibrium. A change in pressure is a disturbance. Quick note, if gases are present. And changes in temperature can also disturb equilibrium. What the critical thing to focus on of these three, as far as understanding goes, is you want to understand how changes in concentration disturb equilibrium. Because one of the things you'll see is changes in pressure and changes in temperature are both kind of just changes in concentration anyway. So if conceptually you can really zero in and focus on understanding changes in concentration, understanding changes in pressure and temperature will come naturally, right? So what I would like to do at this point is to do a few examples where we look at a chemical equilibrium and evaluate how it's going to shift, all right? So let's do a few examples. So predict the direction actually, hang on. Predict the direction of the shift and how the concentration of products and reactants will change when all right, when first let's look at first I got to give you a chemical equation. So let's look at the neutralization of HCl and NaOH. All right, and let's predict the direction of the shift and how the concentration of products and reactants will change when HCl is added. All right, so the fundamental question that you need to ask yourself is, when you add HCl, is that going to affect the rate of the forward reaction or reverse reaction? And for HCl, it is on the reactant side, so this will affect the rate of the forward reaction. That is the rate that's going to change. If you increase the amount of HCl, increase its concentration, how is that going to affect? Is the forward reaction going to speed up or slow down? Well, there's going to be more collisions on the reactant side, right, for the forward reaction. So that is going to increase the rate of the forward reaction so that temporarily it will be greater than the rate of the reverse. And if this forward reaction is reacting faster than the reverse, then that means we are going to experience a shift away from the forward reaction towards the reverse reaction. We're going to experience a shift to the product side, which is a shift to the right. All right, so we are going to see this equilibrium shift to the right. Which is going to result in an increase in the concentration of our products and a decrease in the concentration of our reactants. All right? So that is the prediction we make based on the Chatelier's principle if we increase the amount of HCl in this reaction. All right? Let's do another example. Oops, let's keep our chemical equation though. What's going to happen to the equilibrium if we add sodium chloride to this mixture? Well, if we add sodium chloride, the first question to ask yourself, again, is this going to affect the forward reaction or the reverse reaction? And since sodium chloride is on the product side, this is going to affect the rate of the reverse reaction, all right? This is going to affect the rate of the reverse reaction. Now ask yourself, is adding sodium chloride going to increase the collisions of the reverse reaction or decrease them? It'll increase them. If it's increasing collisions, it's increasing the rate. That means adding NaCl to this equilibrium will increase the rate of the reverse reaction. That will result in a shift to the left. So adding NaCl, it says to predict the direction of the shift. This will shift to the left, which means that we are going to see an increase in the concentration of reactants, because we're shifting to the left, we're making more reactants, and a decrease in the concentration of products. So that's what happens when we add NaCl. Let's do another one. Let's see what happens when sodium hydroxide is removed from the equilibrium. All right, this is a kind of a different effect. First, we identify where sodium hydroxide is. It's on the reactant side, so this is going to affect the rate of the forward reaction. But you have to ask yourself, how? How is this going to affect the rate of the forward reaction? The answer is sodium hydroxide. If you remove it, you're going to have fewer collisions. That means that the forward reaction is going to slow down with fewer collisions with sodium hydroxide. So removing sodium hydroxide is going to make the rate of the forward reaction less than the rate of the reverse reaction. And so this equilibrium will experience a shift to the left, because all of a sudden the forward reaction is slower, the reverse reaction is faster, and so it's going to force material to the left of this reaction. All right, we are going to experience an equilibrium. This equilibrium is going to experience a shift to the left. And a shift to the left means that there will be an increase in the concentration of reactants and a decrease in the concentration of products. All right. So we've got one more before we move to a different reaction. And that is predict how the equilibrium will shift if H2O is added. Now, before you jump and start doing the logic for this thing, I want to warn you up front, this is a trick question. This is a trick question because look at the phase of water. It's a liquid, all right? Remember that for equilibrium constants, if we were to write the expression for the equilibrium constant for this reaction, it would be equal to the concentration of sodium chloride over the concentration of HCl times the concentration of sodium hydroxide. You only include species that are in the aqueous phase or the gas phase in your equilibrium constant. Liquids and solids do not experience a change in concentration because they're pure substances, so they're not included in the equilibrium constant. That means that when O2 is added, the result is no shift. All right, anytime, all right, so this is important, adding or removing liquids or solids does not disturb equilibrium. All right, so that is the trick to watch out for. Anytime a solid is added or a liquid is added or removed, you're not going to disturb equilibrium. There will be no shift. So watch for that as we move forward today. Watch for it when you run into this on the final. All right. Okay, let's do another. We're going to look at two more reactions. All right, the first is a decomposition reaction, the decomposition of solid calcium carbonate, calcium carbonate into solid calcium oxide and carbon dioxide. All right, and note something that I want to point out here. This reaction is endergonic. All right, this reaction is endergonic. Now, you'll see where that comes into play in a moment. First, exact same question as before. Predict the direction, the shift in equilibrium, and how the concentration of the products and reactants will change. Predict how it'll shift when we add calcium carbonate. And if you have a good eye sniper, you are going to notice that this is a solid phase. Adding solids, removing solids do not affect the position of equilibrium, so there is no shift. All right? Just like we saw with a liquid in the previous example. So adding more solid doesn't affect equilibrium. There's no shift. All right, let's do another one. This one's going to be different. What happens when you increase pressure? Now, if your gut instinct says we're changing pressure and we have a gas in this reaction, I bet these two things are connected. Your gut is spot on. The question is, how are they connected? How are they connected? I have to do a little algebra to show you. So, a little aside, we know we have the ideal gas law, right? PV equals nRT. Watch what happens when I divide both sides of this expression by volume. First it cancels off of this side, then the expression changes to P is equal to N over V times RT. What does N stand for? Oh, excuse me. In this mathematical equation. N is moles. What is volume usually when we're using the ideal gas law? liters, right? Moles per liters. This is literally molarity. You can substitute it in, rewrite the expression to say that the pressure of the gas is equal to the molarity of the gas times RT. And notice that pressure and molarity are directly proportional. If pressure increases, molarity increases. If pressure decreases, molarity decreases. So when you see increase in pressure, you should read it. You should read this as an increase in the molarity, which is concentration, right? Increase in the concentration of every gas. All right, that's what we're dealing with when we're dealing with an increase in pressure. So if we have an increase in pressure, that is going to affect CO2. That's the same as adding CO2, because at a higher pressure, you're going to have more collisions with carbon dioxide. As a result, the rate of your reverse reaction is going to be greater than the rate of your forward reaction, because we've just increased our concentration of our gaseous product. If the reverse reaction is faster, we're going to see a shift to the left. So we see a shift left, which means that we're going to experience an increase in the concentration of reactants and a decrease in the concentration of products. All right, and that is how you handle pressure changes. It'll only affect your gaseous reactants and products, and an increase in pressure increases the concentration of the gases in your reaction. All right. We have one last example concerning this reaction. Let's predict which way the equilibrium will shift if we increase temperature. Now, whenever you're doing a Le Chatelier's principle problem and you're asked to predict the direction of a shift when temperature is increased or decreased with a change in temperature, you have to properly understand what it means if a reaction is endergonic or exergonic. An endergonic reaction is one where energy is absorbed during the process, right? Exergonic is energy is released. When energy is released, energy is a product of that reaction, can be considered a product of the reaction. When energy is absorbed, as is the case with this endergonic reaction, energy or heat is considered a reactant. So an increase in temperature is the same as adding a reactant, because heat is a reactant, like an invisible reactant in this reaction. So an increase in temperature means that we're adding more heat, which is on the reactant side. So that means that the rate of our forward reaction will be temporarily larger than the rate of the reverse. If the forward reaction is faster, we're going to experience a shift to the right. So when heated, this equilibrium shifts to the right. Which will have the following results. It will increase the concentration of our products and decrease the concentration of our reactants. All right, and that is the last question I'm going to ask about this chemical equilibrium. We're going to do one more just to be thorough, but after this, you'll be able to tackle any Le Chatelier's principle question out there. All right. Let's look at, oops, what am I doing? There we go. We still want to predict the direction of the shift. But now for the reaction between nitrogen gas and hydrogen gas, which react reversibly to make ammonia. And this reaction is exergonic. All right, so let's do these examples. Sorry, Blake, I just saw your question. Here, let me pull back just a second there. Yes, so for the calcium carbonate reaction, a decrease in temperature. Oh, sorry. For this one, yes. A decrease in temperature will totally add products here. All right. So let's do a few of these. Whoops. There we go. So what'll happen to equilibrium if we remove N2? All right, so we have N2, which is on the reactant side of this reaction. If we remove it, this is going to affect the rate of the forward reaction. And if we pull it out of equilibrium, if we remove N2, yeah, dude, well done. Good job predicting it. If we remove N2, it is going to slow down the rate of the forward reaction. So the rate of the reverse reaction will be temporarily faster, resulting in a shift to the left. This is going to result in an increase in our reactants and a decrease in our products. Let's look at the flip side of the coin of Blake, of what your question was now. What would happen if we increase our temperature? Again, first we need to know how to treat our note here that this is exergonic. Exergonic means energy is being released, and so heat can be considered a product of this reaction. We can write it in on the product side. So if we're increasing temperature, that means we're adding heat. This is going to affect the reverse reaction rate. And if we're adding a reactant to the reverse reaction, which is essentially what heat is in this scenario, we are increasing the rate of the reverse reaction. It will be temporarily faster than the rate of the forward reaction, and it will result in a shift towards the reactants. Adding heat will. This will increase the concentration of our reactants, decrease the concentration of our products. Let's do one last example. What happens if we increase pressure? Like we saw with the last example, this is going to, an increase in pressure will result, this is another way of saying it's going to increase the concentration of gases. The problem that we run into here is this reaction has a lot more gases in play than the previous one. The previous reaction only had one gas, so it only affected one side of the equilibrium. But here you'll notice that we have 3 different gases in this reaction, which means everybody's going to get more concentrated. Both sides will get faster, but the question is which side has a greater increase to its rate. And to assess that, you have to look at the stoichiometric coefficients associated with your gas. On the reactant side, there are 2 moles of gas. Sorry, on the product side. On the reactant side, we have a total of 4 moles. We have 4 moles of gas on the reactant side. That means that the rate of the forward reaction is going to increase more than the rate of the reverse does, because there's more gas. It's more heavily influenced by this change. And if the rate of the forward is greater, then we're going to experience a shift to the right, which means a decrease in the concentration of our reactants and an increase in the concentration of our products. All right? And now you've seen it all. You've seen everything that Le Chatelier's principle can throw at you, and this does indeed bring to a conclusion Chapter 8, which leads us straight into Chapter 9. Oops. let's see. There we go. All right, new chapter, new topic. Though you'll see that it is definitely related to chemical equilibria, and we will draw upon what we've learned in chemical equilibria in our discussion of Chapter 9's topic, which is acid-base chemistry. All right. Now, let's pull that down a little bit. There we go. There we go. Much better. All right. Chapter 9 is about acid-base chemistry. Super cool chapter. Super interesting topic. It's one that feels more familiar because we acids have been, and bases to some extent, but really acids have been popularized in media, from the blood inside the xenomorph in Aliens to that famous bathtub scene in Breaking Bad. So this feels like a more familiar chapter, but we need to start at a very fundamental level. We need to know what an acid is and what a base is. Turns out that the answer to that question depends upon who you ask. There are several different definitions for acids and bases, but the one that we're going to start with comes to us from a dude named Svante Arrhenius. All right. Svante Arrhenius won Best Mustache in Chemistry every single year of his life. It was never contested. Look it up and you'll see why. Look up his picture. He gave us a very fundamental definition of what an acid and a base is. The Arrhenius definition of an acid is this: an acid produces hydronium, which is a polyatomic ion, when dissolved in water. And he said that a base produces the polyatomic ion hydroxide when dissolved in water. All right, so an acid produces hydronium when dissolved in water. A base produces hydroxide when dissolved in water, according to the definition given to us by Arrhenius. All right. So, if we take this definition, if you had an acid, I'm just going to be very generic here. I'm going to call it HA, and you place it in water, it would react to produce the polyatomic ion hydronium plus A minus. This is, you'll notice, the what's left over from HA. If you had a base, the way a base forms hydroxide when dissolved in water, this is not the only way, but this is the most common way. Bases are usually metal hydroxide, so there's some metal cation paired with hydroxide in the aqueous phase. And bases most of them. We'll talk about the exceptions when we get there. Right now, we're starting general. We know that aqueous ionic compounds separate into their cation, oxide, anion. And again, this is how your metal hydroxides will form hydroxide when dissolved in water. It's from two ions separating, whereas your acids form hydronium by directly reacting with water. Non-metal hydroxide bases also will react with water to produce hydroxide, much like the acids do, but most of our examples in this class are of metal hydroxide, so that's why I chose to write it in this fashion. Now, something that's very important to note about the Arrhenius definition, is this. Arrhenius defined acids and bases by what they produced. All right, he defined acids and bases by what they produced, but that is not the only thing you can look at. And our next definition, and our next scientist team will come up with a definition of acids and bases that define them not based on what they produce, but based on their reactivity. All right, so we'll see that distinction, that difference, in our next definition, which is the Bronsted-Lowry definition. Right, so you have the Bronsted-Lowry, whoops, that should be an O. The Bronsted-Lowry definition for acids and bases work like this. An acid, Bronsted-Lowry defined as a proton donor, and a base defined by Bronsted and Lowry is a proton acceptor. All right, so for example, if I gave you a chemical equation like the following, and asked you to identify the acid and the base on the reactant side, you would need to use the Bronsted-Lowry definition. All right. One of the things you'll notice is, so acids donate a proton. If you look at HCl and ask, what does that thing become on the product side? The answer is, oh, well, Cl minus. The way it got from HCl to Cl minus is by giving away one of its H's, not just an H, but an H plus. You'll notice that it starts neutral, but ends with a negative charge. That means in addition to losing an H, it lost a positive charge, which makes it a hydrogen donor. If you look at the definition, the Bronsted-Lowry definition for a base, it's a hydrogen acceptor. And when you examine water and what happens to water, water, H2O, turns into hydronium, H3O+. You'll notice two key changes. First, you start with 2 hydrogens and with 3, so you've gained an H. You also start with no charge, and you end with a charge of positive 1, so you've gained a positive charge, which means that water has been a base, a hydrogen acceptor in this reaction. All right, so HCl is your acid, H2O is your base. I want you to consider another reaction, one between aqueous ammonia and water to produce ammonium and hydroxide. Now, let's identify our acid and our base in this reaction. Well, when you look at ammonia, ammonia is becoming NH4 plus, ammonium. It's gained a hydrogen, it's gained a positive charge. So ammonia has been our proton acceptor, making it the base. When you look at water, water starts H2O, ends as hydroxide. It has lost an H, and it's lost a positive charge. So water in this reaction has been our proton donor, making it our acid. All right, so with the Bronsted-Lowry definition of acids and bases, we don't look at what they make, we look at how they react. All right, we look at what they're doing in the reaction. Acids are donating a proton, H+. Bases are accepting a proton, H+. Now, I want to point out two things. First, the Bronsted-Lowry definition of acids and bases is not in conflict with the Arrhenius definition. Case in point, if you look at HCl dissolving in water, it makes hydronium, which is Arrhenius' definition of an acid. If you look at ammonia, NH3, dissolved in water, it makes hydroxide, which is Arrhenius' definition of a base. So it's not like these two definitions are at war with each other. They're actually in perfect agreement. They just describe different things. The Arrhenius definition describes the product when mixed with water, and the Bronsted-Lowry definition describe the way that the compounds known as acids or bases react. All right, so it's a difference in focus that describes the same phenomenon and is in agreement. All right, so they're not fighting. They're totally on the same page. They're just looking at different things. The second thing I want to point out about this page before we leave it is I want to ask a question about water. Is water an acid or a base? Is water an acid or a base? Now, when you look at the first reaction that has water, water's reacting with HCl as a base. When you look at the second reaction, water's reacting with NH3 as an acid. So you might be wondering, well, water's both an acid and a base, but that answer is not correct. It's actually just as wrong as saying water's just an acid, water's just a base. Saying water is an acid and a base, also incorrect. It's closer to the truth, but it's not wholly accurate. You see, because the term acid and base is not an identity. Acid is not an identity. Base is not an identity. Acid and base is a role within a reaction. So asking, is water an acid or a base, is like asking, am I a son or a father? Son and father aren't identities, they're relationships to other people, right? I am a son to my father, In that relationship, I am a son. I am a father to my son. In that relationship, I'm a father. Acid and base is the exact same thing. It describes a relationship within a specific chemical equation. So, when asked, is water an acid or a base? The answer is, well, show me a reaction. I need to see how it's reacting within the context before I can answer one way or another. Now, there are some compounds that are very strong acids that almost always react as acids. There are some compounds that are very strong bases. They almost always react as bases, but that doesn't mean they only react that way. And so before you can make that assessment, you really need a chemical reaction so that you can determine the relationship of that compound based on how it's actually behaving with respect to another compound. All right. Okay. Let's do an example. I realize we're almost out of time here, but we can push a little farther. So, identify the acid and base in each reaction. All right, first reaction. Identify the acid and base in the reaction between aqueous HF and aqueous NH3, reacting to produce NH4 plus F minus. When you look at HF, HF becomes F minus. It is clearly donated H plus. It's lost a hydrogen, it's lost a positive charge, which makes HF the acid. When you look at an H3, oops, sorry, I forgot a positive charge right here. There we go. When you look at an H3, it's gained, going from reactants to products, it's gained a hydrogen and it's gained a positive charge. So it has accepted a proton, which makes it a base. A base is a proton acceptor. An acid is a proton donor. All right? Let's do the same thing for this reaction, a reaction between aqueous ammonium and fluoride. That produces, for its products, hydrofluoric acid and ammonia. All right. Let's figure this out. Acid or base? You'll notice ammonium in this reaction becomes ammonia. It starts with 4 H's and a positive charge. It loses the positive charge and a hydrogen. That makes it a proton donor, which means we're dealing with an acid. Fluoride picks up a hydrogen over the course of this reaction and a positive charge. You'll notice it starts negative, ends neutral. That makes fluoride a base. Now, I'm sure most of you, I'm sure all of you actually, have spotted the fact that I really drew this first arrow wrong. There should be equilibrium arrows. You'll notice that these two reactions, that the reactants on one are the products of the other and vice versa. All right? The relationship between HF and fluoride, and the relationship between NH3 and NH4 have special names. These are called conjugates. So ammonia and ammonium are conjugates, as well as hydrofluoric acid and fluoride are conjugates. All right? Ammonium is called the conjugate acid because the reason why it's called the conjugate acid is because it is the acid of the reverse reaction. Fluoride is called the conjugate base because it is the base. Oh, that's not a good contrast. How about this? No, not that. This. No, let's go back with purple. Because it is the base of the reverse reaction. So your acid turns into your conjugate base, and your base turns into the conjugate acid. And again, these names, conjugate base, are based on the role, on the function that they serve in the reverse reaction. All right? Every acid-base reaction has two conjugate pairs, a pair of acid conjugate base, base conjugate acid. All right. Excuse me. That is going to do it for lecture today. I'm looking at what comes next, and it will take more than 5 minutes to cover it. So I'm going to go ahead and pause here. We'll pick up talking about more acid-base chemistry on Thursday. So that's it for now. I'll catch you guys all in lab.